So welcome to lecture 15 of MCS 471, numerical analysis. So in the previous lecture, we introduced the problem of interpolation, and we defined the coefficient problem and the value problem. So the main point of today is that we will see an algorithm, one algorithm, to solve both the coefficient problem and the value problem. This is called Newton interpolation, and it relies on divided differences. So in this lecture, we start out with the problem of adding more interpolation points, what you could call incremental interpolation. We add more interpolation points in order to get a more accurate approximation. So the goal of this lecture is indeed to study Newton interpolation, but in the last part we will see an expression for the interpolation error. And we will give a rule, what is called an X-term rule, that will help us to decide when to add one more interpolation point. So let's look to incremental interpolation. So here is the problem statement first. What is our problem? We can see this topic of interpolation as a data compression topic. We have data and we want to compress it or kind of represent it by a much simpler function. And the simplest functions are the polynomial functions that we will be using. We can also see this that we have some difficult function and we want to replace that difficult function by a polynomial. If we impose the interpolation conditions, then this means that we have a number of xi values where we are going to evaluate our function, or these are points where the xi's are points. It could also be time, for example. These are points where we have measured, for example, temperatures. So every morning we measured the temperature, and we want to represent that entire collection of data by, say, a polynomial. So it is important in this lecture, and actually in all the topic of interpolation, is that these points where we take our evaluations or where we take the measurements are all distinct from each other. So last time we proved that if this condition is met, if all the points are mutually distant, then the problem has a unique solution. So there is this uniqueness problem that we covered, that we solved last time. Here we now have two questions. If we are going to add points incrementally, how can we do this efficiently? The algorithms that we considered last time were actually not that friendly towards adding new interpolation points. So the algorithms that we covered were quadratic in n, but we don't want to redo that. So if we are going to add a new interpolation point, we would actually like to have only a linear amount of work. So we have the algorithmic question, but then we also have, actually most importantly even, what is our criterion to decide if more points should be added or not? And that is a numerical criterion, not a very precise criterion that we can apply. Here is an example. So it's again the sine function of last lecture, but now I picked 4 equidistant points. And you see that towards the middle, between minus pi over 3 and pi over 3, actually the polynomial, the red polynomial, approximates the blue sine function quite accurately. But we have two bulges at the left and at the right. So what we actually want to do is we want to add one more point to the left. So here is the interpolation at 5 points. So then actually it looks quite good up to the left, although the middle is actually now not so good anymore. But the bulge at the right is actually what bothers us most. So we're going to add one more interpolation point in between pi over 3. So pi over 3 is over here, and pi. So we're going to take the midpoint of this and use that as an extra interpolation value. Here is what we have now. So you can see that the red almost overlaps entirely with the blue. And these are equidistant points. So in a way, we skipped the origin as a point, but by pure, I wouldn't say luck here, but by the shape of the polynomials, by the symmetry that's also in the polynomial, we actually have somehow the origin for free. All right, so here we decide our accuracy by looking at it. But just plotting a function is actually quite time consuming as number of evaluations is concerned in the rendering. We would like to have a more precise, so also looking at things is a little bit subjective still. So we would like to have a better criterion to decide whether this is accurate enough. So that will be at the end of this lecture. But let us first look to a new algorithm that will efficiently deal with the issue of incremental interpolation. Here it is. We go to a new form of the interpolating polynomial. So we call it the Newton form. So remember we did this thing also with Lagrange. So we went to a new form. Here our new form is attributed to Newton, and it takes a very specific form. So we have not yet fully defined it, so the coefficients are not defined, just represented as symbols. But you can kind of see the incremental nature of things already. So if you read this polynomial, and actually we now read the polynomial starting at a constant term, so this f with the square bracket x naught is a number. Here we have the number that involves x naught and x1. And you can see that the factor x minus x naught occurs everywhere. So you already know what the x naught is. It is the function value at x naught. And the second coefficient will be computed by what we call a divided difference. So the shape of this polynomial, you can see it's a polynomial of degree n, yes, not n minus 1, because you see we start to count from 0 and we go all the way up to n minus 1. So this is a polynomial of degree at most n. So this coefficient may often be 0, not often so much, but there are circumstances where this coefficient is 0. So this is a polynomial of degree at most n. And the divided difference coefficients will be ensure that the polynomial interpolates, so that the interpolating condition is satisfied. So the important point as far as the problem of incremental interpolation is hereby solved. So this is the essential point of Newton interpolation in relationship with our problem where we started with. So that's worth one extra slide. I should also point out that we order the points x0, x1, x2, but as in the example where we started with, there is no enforced order. It's not so much that x1 should always be at the right of x2. No, the order of the points can be arbitrary, so they shouldn't be sorted. All right, so this is the summary of Newton interpolation, except that you can't really do this yet. So we still have to define what are these divided differences. Here is their definition. So the divided differences are defined recursively as follows. So if there's only one point involved, then the divided difference is just a function value. We also have the condition that the xi's are different from the xcj's. So if there are 2 points involved, then we divide the difference of the function value over the corresponding difference of the points xi, xj. And in general, we have the recursion that the divided difference for an arbitrary number of points is obtained by the divided difference, the difference of two divided differences of 1 point less. So you can see the structure. So for here we end at j minus 1. Here we start at I plus 1. So we have 1 point less. So we have two base cases. You can implement this as a recursive function, but we will not do this. So the formulas are very symmetric, very much like Neville interpolation. How are they organized? Well, we start with our points as the first vector, then the function value in the second column of the table here, and then we compute the divided differences. So we compute the divided differences, we can compute this column by column, or we can compute this along the diagonal. So actually it's the diagonal that we need. So the diagonal of this table of divided differences, this will be the coefficient vector in the Newton form of the interpolating polynomial. So what we care about is the diagonal of this table. So this is an n-square algorithm, but we only need n numbers, the coefficients of this polynomial, and we can also be more frugal with our storage. So that's here the last line. So as soon as we compute f01, we no longer need f1. So we can actually put at the place of f1, we can put f01. Now, also with regard to our original problem of incremental interpolation, if one point is added to it, so if point x4 comes in, then actually we only need to compute one row of the one extra row of this table. And that is linear. So the cost of adding one extra point is actually the cost of computing one extra divided difference. So this is the algorithm, already enough for us to do this on paper, but let's go to the implementation. So algorithms in this course are defined by Julia functions. So we will compute all divided differences in a double loop. So the recursion is now rephrased using the loop indices. So we have the I that runs over the rows in the table. The j goes up to the diagonal. So indexing is starting at 0 and going to I minus 1. So we actually have I steps there. We can immediately see that we do 2 differences and 1 division. So we do 3 arithmetical operations in every step. We have a double loop, so the cost is quadratic in the total number of points. One recognizes the formulas, so we have the common points are actually now all ordered up front, so we can relabel. So this is another way of saying that the order of the points doesn't matter, is that if you relabel the interpolation points, the interpolating polynomial remains the same. The symmetry again, the interpolating polynomial is invariant under the order of the representation of the points. So this is the algorithm on paper in pseudocode, and that's all there is. Not quite. So I said at the beginning of this lecture that the algorithm that we are considering solves both the coefficient and the value problem. So the Newton form gives us a very nice representation of the interpolating polynomial. So the representation of this interpolating polynomial is written here. So that's the coefficient problem. Now for the value problem, recall from the very beginning of the course, so this was the basics, the efficient evaluation of a polynomial. So this is exemplified here with an example with 4 points, so a cubic polynomial. So if you look at it given by the Newton form, then that's not a good way to evaluate the polynomial. So the evaluation would not use the Newton form, but would use the nested Horner scheme. So we can save, as you like, the multiplication with these differences here. And we can interlace the multiplications with the additions. So the basic algorithm to evaluate a polynomial of degree n, if you don't do it right, it costs you n square operations. But if you do it following the nested Horner scheme, you can do this in a cost that is linear in the degree. So very specifically, we have n additions. So here we have a polynomial of degree 3. We have 3 additions, and we have 3 multiplications. And because we work here with the interpolation, we have 3 extra subtractions. All right, so this is summarized here. So we have solved both when we compute the table of divided differences, we have the Newton form, we have the coefficients of the Newton form. When we remember the Horner scheme, we actually have an efficient algorithm to evaluate the polynomial. So in the Jupyter notebook that posted, was used to make the pictures at the beginning of this lecture, you will see that if we have the coefficients, we can define a Julia function to evaluate the polynomial. All right, let's now look into Julia. So the algorithm actually is so simple that everything fits on one single slide. So we have the documentation string for the divided differences that take into input two arrays, and on return is another array. So that's the array of the divided differences. It is a very simple and basic algorithm. It follows very close the pseudocode, except that here one has to be a little bit careful with the indices. So the Julia arrays, they all start at 1. So it's so very natural to work starting at 0 in the context of polynomials. All right, then the evaluation using Horner scheme is actually even more basic. The font can be larger. So we have the interpolation points, the x vector. Then we have the divided differences. And then we have the point labeled here as xx. And you can see that here to evaluate, we have a number of operations that is linear in the length of the numbers. Okay, so this is the algorithm. What is still lacking about, so these are the two algorithms to evaluate and to compute the divided differences. What is still lacking is a formal proof that the Newton form is actually interpolating. We went through the formulas, to the proof of the formulas for Neville interpolation. You can look into the textbook for the justification why this Newton form is interpolating. We will not go here. It's time for a first exercise or a first demonstration here, how things are combined. So we have now all the data, we have the points, we have the function values, and then the point where we want to know the value of the interpolation problem. So here you see the example. This function Newton solves both the interpolation problem and the value problem at the same time. So you want to know the value of the polynomial once, that's the value problem. You make up the divided differences and then you run Newton's method, run Horner's scheme, evaluating the Newton form. Now, if you run here Newton, you also get the divided differences back. So if you have to evaluate the interpolating polynomial at another point, then you only need to do the Newton form only once. You do not need to recompute the divided differences. Or you could say that the divided differences are actually replacing the function values. You see the data compression element that comes in here. Instead of working with your entire data set, you actually now have the divided differences. So here the divided differences are just as long as your data set, but you remember that we had a difficult function we started with, the sine function, and we sampled it at certain points. So instead of looking at the entire sine function, we're looking at some points on the sine function. All right, then time for a first exercise. So the exercise recommended solution is via using the Julia functions. But this is still an exercise of paper and pencil. We have a polynomial that we want to interpolate. So in a way, this is kind of a benchmark example. So this kind of deals, this type of example is kind of for us to reassure that our code is correct and actually that we understand the algorithm, because we remember the uniqueness of the interpolation problem. So we have a quadratic and we are going to use 4 points to interpolate that quadratic. Now actually with 3 points we will actually have already the quadratic polynomial. Now in the first part of this exercise I can answer what is the answer to the first part. Well, the last divided difference that you compute will be very small, and that is because of the uniqueness of the interpolation problem. So in exact arithmetic, if you do this by hand with exact rational arithmetic, then the last divided difference is equal to 0. If it would not be 0, then you would have a cubic polynomial that interpolates at the same data points at the given polynomial p. So, and that would violate the property of the uniqueness of the interpolating polynomial. So we compute the Newton form. So in a way, this is kind of a shifted basis. So the polynomial is here given in the standard basis, but we are representing the polynomial now in the shifted basis. So x minus x naught, x minus x1, x minus x2, x minus x3. So it will be a quadratic polynomial. And this is where you have to use the explanation of the uniqueness. So it cannot be a cubic polynomial. The Newton form is also a quadratic. So if you compare the Newton form with the given polynomial, then you will see that both of them are actually quadratic polynomials. All right, let's now go into the remaining part. When do we decide now? When we take an extra point, we can get a more accurate interpolating polynomial. But when and how do we decide this actually? So let's look at the interpolation errors. So let's first remind us to the conditioning of the interpolation problem. So in theory, as long as the points are different from each other, the solution is unique. Fine, but what if the points are close to each other? So if something cannot be 0, so all the mutual differences cannot be 0, that's a condition, a mathematical condition for the uniqueness. Now it will break down when things are getting close to 0. And one can see this already numerically. If you compute the interpolating line through points, then if the x0 is very close to x1, you will have huge coefficients. So you have kind of the same problem again, where there is a small change in the input x0 or x1, then that will lead to a very huge change in the output. So that was what we defined a bad condition number. All right then, see what happens if you take equidistant points and we interpolate the constants. And we take equidistant points, first for 5, then 10, 20, 40. See what happens to the errors in the divided differences. So these errors in the divided differences, they need to be all be 0. So actually this will be a table of zeros, but some zeros actually not going to be zeros is because of rounding. Now there's actually little rounding that will happen here because you will just subtract 1 of 1. So in a way, this will be an entire 0 table. So if you do not know the uniqueness of the interpolation problem, this seems to be an absurd bug, but it is not. So everything should actually be 0. Okay. Now let's look at the interpolation error again. So we ended with 6 points, 6 points which are actually not equidistant, or we got the 0 for free, seems like. Now it looks very good, except perhaps a little bit we see most blue, so the red is opposed over the blue. We see more blue at the endpoints. Here is a more accurate picture if you're interested in the error. So we look at the shape, we plot this difference between the sine function with the interpolating polynomial. What you indeed see is that this error is now actually 0 at 0. So here this is kind of the free point that we got. And of course, this is kind of a bonus. We didn't impose this, and quite naturally, the interpolation error through 6 points has actually 6 roots. The interpolation error is 0 at these 6 roots. You also see the wobble. So in the interval -2, 2, it actually goes very well. So you can see that we have kind of a band. So this is kind of the upper bound on the error. So we have a quite good approximation. So we have 2 decimal places that you can read off. Not bad for 6 points. But then at the end points, the error starts to go larger and larger. So we go more deeper in this phenomena next time. So we still have one more lecture on interpolation, so we're not done yet. So we were very happy with the interpolation through 6 points, but here I'm indicating already that that might be a problem. In particular, we may not have uniform error bounds. Okay, so this is a dense slide, but we are looking for an expression of the error function. So the error function was defined as the difference between the original function and the interpolating function. What we observed in the picture is that that error function has as many roots as the interpolation points. So we have n plus 1 interpolation points. So here they are again. So that's why this slide is a little bit dense. It's self-contained. So the error function has n plus 1 roots. And therefore you can actually write the representation as this polynomial that has the differences. So it looks a little bit if the x is 0, x1 is 1, xn is n, it will be the Wilkinson polynomial. And that dreadful polynomial we encountered in the second exercise collection. All right, so that's already actually very good. So we know the shape of this error function. Now let's look at what is the constant. Can we represent this as a more neater representation? And we can. So we look at the error function. So we have now four functions. We have the given function, the interpolating polynomial. We have the actual error function. And then we have this kind of curly e, that is the fourth representation. So this is the polynomial. That's probably the most important thing. So the error function is in general not a polynomial, but we can kind of represent it by a polynomial. And how do we do this? We look at the derivatives, and if we take derivatives and take derivatives n plus 1 times, then actually the interpolating polynomial drops out. So we look for essentially the error. So there's a fifth function coming in here, this capital F. And it seems to get more complicated and more complicated. But as we take derivatives and derivatives, the interpolating polynomial drops out. And we can find an expression for this big K. So we are after the big constant K in our representation of the error. So this is given by a function. It's assuming that the function f, and this is where we are reading now completely in the opposite way. So let's read the first line of the slide. In order for being able to take so many derivatives, the derivatives must of course exist and they must be continuous. So this is what is called continuously differentiable. So we're using calculus again. So if we have now this k that is given as the ratio of two functions. I'm sorry. So the k, is actually proportional to the n plus 1 derivative. Now, from a result from calculus, there exists now some value. So in order for this to be 0, there is a root. And that root will give us the value for k. So what is most important here is what I'm going to box in now. So that is the expression for this big K. So that's the main result of the slide, that the interpolation error has n plus 1 roots and has this form here. So we have the form k times this product of all the differences with the interpolation points. So it is this interpolation constant k that is very important. So here we can now write the interpolation error consisting of three factors. So we have all the differences, which makes that the error becomes 0. we have the n+1 derivative sitting in there. And that's kind of another proof that when you interpolate a polynomial of degree n, then the error has to be 0. So the fact that you get the n+1 derivative, and now forget about this alpha, the root, this is for any x. So the error will be 0 if the f is a polynomial of degree n or less. So that's also a check that this expression is kind of the right expression. And then we have the n factorial bound. So the n factorial bound is actually very nice because it actually means that this is a factor that appears in the denominator. So that will make the magnitude of the error actually be very, very small, since that factor goes extremely exponential. So we can actually have a magnitude on the error bound. So the error bound is actually bounded by the bound on the n+1 derivative. We have this maximum, and then we also have the length of the interval. How do we get the length of the interval? Well, that's a bound on this polynomial here. Now notice you get the n+1 factor here again. So the m we typically don't know, but it's a constant. And the b minus a we actually do know. So if the interval is 0, 1, then actually you shouldn't worry about this exponent n+1. And this is where then on the interval 0, 1, you can hope that your error is actually bounded, grows actually very fast to 0. Or actually goes very fast to 0. So that's a very encouraging result. Now, one practical result, yes. So remember the original question from the start of this lecture. When do we decide to get to use an extra point? Well, we look at the last divide difference that we computed. But by the way, so this I'm hammering on this uniqueness question, but the Newton interpolation also gives us an algorithm to detect whether our data is polynomial. So if you are interpolating and you see at some point that the divided difference are getting to 0, and you've seen this with exercise 2 when we were interpolating 1 and actually everything is 0. So it didn't really matter for how many points we did this. So here we have the next term rule that will tell us actually what is this. You could see the last divided difference as an approximation for the constant k. So, and that is the next term rule. I'm actually writing here the Newton interpolating polynomial again. And at this point, I should actually say that this is actually very resembling Taylor. So Taylor uses differences, so the uses derivatives. So the Taylor expansion of a function takes exactly that same form here. So you could interpret the Newton form as an approximation for the Taylor series. Now, it will go on forever and ever with the Taylor series, but if we are interpolating a polynomial, then actually we have the Taylor representation relative to a basis of picked interpolation points. Now the point of this slide is, of course, use the last divided differences to decide whether you need an extra point or not. Here is the last exercise. We're going back to the sine function. We compute for an approximation with 4 equidistant points. And the next term rule, even if you don't want a next term rule, the next term rule is actually also a bound on the error. So it's called Newton interpolation, the same Newton as Newton's method, because you can see this as an iterative procedure. So you can pick more and more points until you see that the next term rule, so your last divided difference, is actually small enough. All right, so this is the end of this lecture. It's the second middle lecture in interpolation. We still have to resolve one main question. What if you want the accuracy to be as good as it possibly can get, allowing that? How should you pick the interpolation points? Here we assumed that we could, where we picked the interpolation points didn't really matter, and equidistant points are then as good as any, because they are well separated. But there are better ways to do this. And that will be the topic of the next lecture.